Hello, my name is Lindy Humphrey, and this is Lab 3, labeled Circuits of Physics 2212. In this lab, we will use the principles of energy conservation, loop rule, and current conservation, charge conservation plus the definition of steady state, to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. And then going to go ahead and identify the systems, which are the circuit, and the surroundings, which is everything else. A results overview is basically just that the node and the loop rule hold true. And then any potential errors that happen to this lab are just human errors or just being the real life simulation that we had to do in the lab isn't super accurate or just had some issues with it being in the real world scenario. Some main physics principles for this lab that we have to identify is the node rule. This rule is the current flowing into a node must be equal to the current flowing out of it, resulting of the conservation of charge. We also have the loop rule, which is the sum of all the electric potential differences around a loop being zero. This is the result of energy conservation. And then we also have Ohm's law, which is current through a conductor between 2 points is directly proportional to the voltage across the points. And then we have corresponding equations that can go with these. The first part that we had to solve for this lab was charge conservation and energy conservation in a series circuit. Up on the top on the right, we have a picture of basically our diagram and what we're going to be measuring out of. And then at the bottom, I included a picture from our actual lab when we recreated the circuit and got some of these numbers. So we have our I1 being 18.5 milliamps, and then we also calculated that that was 3 volts, or that ammeter was 3 volts. For I2, for that ammeter was negative 19.8, and then negative 3 volts. After we calculated those two values, we looked for the potential differences at the 47 ohms, and we got 0.9 volts. Then at the 100 ohms, we had 1.9 volts. And then the potential differences total was 2.8, which is very close to the theoretical value of 3. So this indicated that we were pretty close, so we're right on it. And then here was our graph that we created. It was an approximate graph of potential versus position around the circuit. And then a question we had to answer was, why doesn't the ammeter reading change, sorry. And then we established that it's the same because it measures the current when it is constant. And as it's constant, it's not going to change. We also had to solve a couple more things. We had to connect the voltmeter across the 100 ohms resistor again and note the reading, which was 1.9 volts. We also had to replace the voltmeter with an ammeter in parallel with the 100 ohms resistor. And then we got 1.59. And then we also had to solve for a couple things with the resistance. And to do so, we have I equals V over R. For the 47 ohms, we calculated where we had the 3 volts for both the 47 and the 100 ohms. And so 3 over 47 is I for that, and then 3 over 100 is the second I. And then the resistance total would just be those ohms added up, and then over 3 again. The last part was the RC circuit, and this was basically the circuit that we had established at different values with the light bulbs. The first light bulb that we tested we established to be 20 ohms, and then with the battery, it was lit for 23.55 seconds. With only the capacitor, it was 18.54 seconds. The second bulb we established to be the 10 ohms after we measured it. With the battery, it stayed on for 73.08 seconds, and then only the capacitor, it stayed on for 81 seconds. And then I also included a picture from our actual lab. And then here was a question answering the only question that we had in this lab, which is the what if. What if we charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? Basically, for the ideal, we'll have no resistance, and then we'll have instantaneous charging. It would reach the full charge pretty much instantly.